we have it. Some things we don't. We're going to make a couple of starts here because this is modified in mid-stride at least once. Incidentally, please feel free to shout if I fail to push these up so you can read. It gets difficult to find out what's down in here when I'm stomping around up here. I should warn you also that I do not intentionally intend to tell any untruths. But you decide on an approach and you go with it. There are many things in here you can argue with easily, and many things that are left out, of course. At any rate, first off, we were going to take this approach like we didn't know this word until we just heard it a minute ago. And I suppose maybe this is all obvious, but to cover the whole gamut here, we'll run through it on what you might expect these two-legged wonders to do. And now here's the point, you see. Somebody's going to say, well, now, wait a minute, you know, you got the wrong place. Well, maybe I have. I don't know. Maybe it's tens of megahertz. Maybe it's a gigahertz. I don't know. Anyhow, in the common terminology that's used in the industry, rectifiers aren't used there. All right? And normally switchers aren't used at 60 hertz, but at any rate. There are a wide variety of, I'll call them oddballs, and that's unfair for the people that have to worry with them, that we're not going to cover in any depth at all. I just mentioned a few here. Some of those will be covered under other subjects and some will not. And I threw this in, and again, it seems obvious, I guess. If you pick up a schematic and you see a diode symbol, well, you say, well, of course, you know, that's where they're going to put one. They need it there to do so-and-so. I did this to lead you into the thing that there are many around, or at least there are diode functions around you don't expect sometimes. In fact, don't want sometimes. And I can't recall the specific lead-in that Dr. Dawes used about it yesterday, but he was referring to structures they use, and sometimes this will rise up to bite you. You were going to tell me when I was supposed to push that up, weren't you? At any rate, if we're talking about a standard device that you go and buy intentionally as a diode, where are you going to look? Of course, in the manufacturer's catalogs, of which there are a semi-infinite variety. And also in some of these other places. Now, there is a catalog now. I just got my copy here last week. These were in the parts catalog, and they're now in a separate catalog for what's in Sandia stores. And I believe that's the name of it, Solid State Devices Catalog. There is, I called it a catalog, and maybe that's unfair, but that's what I called it, that Diane Miller cranks out at some interval, which is a 2120 listing. And if it isn't complete, it isn't her fault. She puts in what we give her. So, as far as commercial things, one-in numbers or other commercial numbers, the rich sources, the data book series. Maybe most of you are familiar with it. Is anybody who doesn't know a data book series? No need to belabor it then, I guess. In that event, I'll just go very quickly through this. This was an attempt to give you a gee whiz on the data book. I picked up the one off the shelf that we have in the office, which is an 81 issue, and ran through these different categories, and this is the way data lists them, and wrote down an approximation, you know, 100 per page, so many pages, that's the way I came up with these numbers. At any rate, there are listed in there 36,000 of these things, separate listings. And the newest number I found in some list was around 6,400 and change. So that the JEDEC numbers, that's right on schedule. The JEDEC transistors, not part of an integrated circuit, are covered in MIL-S 19500, as was mentioned yesterday, and who the qualified supplier is and to what level. So you may find a half a page out for one device, and it looks crazy, and it's all those 67 locations around the world that you see printed on the sticker when you buy a sack of them downtown, you know, and it says made in one or more of the following 300 countries. Now here I'm going to digress from what's where I had planned to go for a moment, if I can find this thing. And this extra little sheet that I gave you, or the two pieces of paper, and it was mentioned there that we were going to say something about structure, and I hadn't really planned to do that. I don't claim to be an artist, and most of you probably know all this anyway. Is there anybody is there anybody in here who has this dying urge to go through this? Okay. This, of course, leaves out many steps that are required, and this is, of course, a very simple gadget. But in basics, it's the same whether you're doing a single diode or an integrated circuit with 10,000 on it. The precision required is a good bit tougher on the one than the other. At any rate, I didn't know where to talk about starting material, and this is as good a place as any. I went back and changed this after I first did it, and what I've shown you here, and I didn't bother to write the word down, I will call EPI. If you haven't heard it, it's a buzzword you'll hear around here all the time, or any place that manufactures these sorts of things. And what is done is to take a starting slice of low resistivity stuff, that's the N plus, and grow on it more of the resistivity that you want to use to build your device. And I was talking to Al yesterday and saying, why do we do that, Al? And Al says that's because you get better control here by growing it than by diffusing into it some resistivity. There's a good bit more abrupt change also between the two types here than if it had been diffused. At any rate, we'll grow some oxide on the top, etch a hole in it. Now I left out several steps in there. You have to put on some varnish and expose it and develop it and leave a hole in it so the etchant can get at it. But at any rate, we etch a hole in it, run it through the tube, and drive some impurities into it, in this case P-type, and we have a diode. Now, we regrow oxide here and then cut a hole in the regrown. Generally, I am told, at least at this level of complexity, that's to be sure we have, I was trying to think of a good buzzword and I don't have one, enough clearance laterally here between the edge of the passivating oxide and the point where the junction comes to the surface. That's particularly true if you do shallow diffusions, because the distance it goes out this way is in proportion to how deep it is. So, at any rate, at this point we do have a diode we can access. We put metal on it, either of this general configuration or with a bump, depending upon what we're going to do with it, how we're going to package it. And I made a note here that if this thing were to be a fast recovery device, we'd probably gold dope it. And that would be done at this point. Put gold in here, drive it in to get the gold into the lattice structure, and then metallize. This is a process that is used mostly at this point, so far as I'm aware, for Zehners. And it consists of placing usually aluminum on top. I left those out. Oh well. That's still epi, all right? Aluminum, it can be a sphere, as I've shown. A little rod, you can evaporate on aluminum any number of ways. At any rate, you need a source of aluminum. You run it through the oven, and it alloys with the silicon. 800 degrees C, 900, somewhere in that vicinity. It forms a junction, aluminum giving you p-type. Now these things have a strange characteristic, and that is at this point here, at the surface where the aluminum disappears down in there, there is something, and that's an arm wave, and I don't know how to explain it, truly. But if you leave that just the way it is, it doesn't make a very good junction. So these generally are etched, and that cross-hatch stuff goes away. That's fine, but it leaves you with the junction exposed to the outside world. Some people put organics, varnishes on there to protect it. TRW claims that they are making their LVA series with an inorganic passivation on there. I can't argue with it. Don't know how they do it. In order not to have to do the etching step, which is nasty and takes up plant space and costs money, somebody said, gee, if the place where the alloyed junction shows at the surface is the trouble spot, why don't we eliminate that spot? And that's what this process does. You take a planar junction, as we were talking about at the top of the page, and alloy aluminum clear through the P layer. We now have a junction down here that's aluminum rich, P to N. Here we have diffused P to N, and at the point where the aluminum disappears down into the material, it's aluminum, which is P, into a P diffused. There's no junction, there's no problem. You don't have to etch it, you're done. Saves some money. Turns out generally to make pretty good devices also. Excuse me. I'm slaving over a hot stove up here. Now there are several others, and in the kinds of things we deal with, normally these two probably aren't used too much anymore. Incidentally, I'm still doing an arm wave on you. I'm showing you cross-sections of a thing that we care about as a finished product. And of course this is reiterated all over in this scale, a pancake the size of the trailer. And you have to get them apart somehow, and there are a number of ways to do that. Present standard, I think, is either saw or scribe and break. At any rate, you take whichever type, and I've shown N all the way through this. It can be a P starting material as well, and diffuse in N, or alloy in N, if that's, I'm not sure that's doable. I suspect it's not. Anyhow, make one diffusion, you've made a junction, you get it apart from its brothers and sisters, and its junction is hanging out in the breeze again. There's no passivation over it. Double diffused. All we've done is to put in a layer from the other side, and incidentally I flipped that on you in the picture, but at any rate, to try to cut down the series resistance we get. Instead of you starting with epi, I kind of did it as an afterthought with another diffusion. Mesa devices are still used many times for high voltage. It's a double diffused structure that's been etched, and this incidentally would be done in the wafer form, not in the chip form. But we've got a slice full of these, and we etch these areas away on all the parts. Now we still have a slice full of these little truncated volcanoes, and we use some process, sputtered glass, thermal oxide, whatever, and coat the junction that would have been exposed to the world if we had just left it in this form. Schottky, we use some in standard kinds of applications, a good deal more in RF kinds of applications. So far as I know, we have not yet written a spec for or used in a system a power Schottky. When the people find out that to get a 7/10 volt forward at 10 amps, they have to accept 50 milliamps leakage at 20 volts, they go away. So far, that's what they look like. They have a nice low forward, but they leak like a sieve in the reverse. At any rate, oxidize, cut a hole in it, put some metal on it. Now that sounds deceptively simple. I'm sure it's not that simple. But at any rate, the metal silicon interface is where the junction is formed. Now, you hear all kinds of numbers, and it depends on which spec for which device you were looking at as to what that forward's going to be. And it turns out there are several answers that are correct, not for a given device, but as an arm wave on Schottkys, because there are a number of different metals that are used here, or combinations of metals, and they will give different forwards. This structure, incidentally, as I say here, suffers from an edge effect, which is that the breakdowns of these generally is not as high as you'd like. A few volts, maybe 15 or 20. Some people want tens of volts, lots of them, 50, 60. At least HP, and others I suspect, said fine, if the problem comes with where the edge of this metal is over the N, we'll change that and we'll terminate it over a P ring that we've diffused in, like a donut, sitting in the surface. Now at the edge of the metal, again, there is no junction. The metal's P, the ring is P, no junction, problem goes away, breakdown goes up, 70, 80, 100 volts. It does have a problem in that if you run a little too much current, the Schottky gives up and this thing starts conducting and you've got a normal diode. So you have to watch how you use these things. And point contacts are really not much used. Some of the old microwave parts were point contact. I don't know whether they still are or not. 1 in 821s, 23s. Yeah, those are still point contact, I guess. They have an extremely low capacitance because you have just a needle point sitting on the surface. But other than that, they don't have a great characteristic. That's a quick once over on that stuff. Now if I can get back, figure out where I was when we sidetracked there. Oh, yeah, we were going to have a little show and tell. These things come, speaking now of diodes as separate identifiable things you can have one of in your hand and look at, and a big range of things, sizes, packages. I've fetched over some hardware. Everybody's seen most of these, but there may be some that are different. There's some manufactured things for show and tell. I'll pass around a magnifier with this one. These are beam-leaded parts. The silicon's about 20 mils square, and then there are little gold beams hanging out in the breeze. And you bond the beams down to the substrate, and these happen to be Zehners. They do transistors the same way. So there we're talking, if mounted on a good substrate, maybe 200, 250 milliwatts. Before I forget, I was cautioned this morning that we were starting with too complicated a device with the diode. We ought to start with the monode. And I rummaged around, and my only example that's ready to go is a dual monode, so you can pass that around.
That's a solution looking for a problem.
This is just a handful of commonly used diode packages. In this shaped box, we're talking 200, 400 milliwatt sorts of things, 1 watt sorts of things, 5 and 10 watt sorts of things. As they get bigger, we'll mention Zehners here in a minute. If I get rolling, there's one at about 250 watts. And there's a rectifier that was, I wrote it on here because I knew I'd forget. That's 4,000 volts, 300 amps.
That ain't big enough.
Yeah, well, one of the things we do over there, of course, is to lie in wait, so to speak, for the unsuspecting customer. Some of them in particular are more fun to zing than others. But it always makes the day when somebody walks in and says, I need a big diode. And we give them that, you see. And these boxes are collections of loose parts. The real-life version of this thing is in one of these boxes. A lot of those are high-voltage packs that we've used for various things or on various programs. I had a picture of a room-size assembly, but now I don't know what I did with it. Too many folders here. I told you this was gee whiz time. There's a high-voltage assembly that Semtech makes, which looks impressive. What did it say? 820 kV, 3 amps. If you can't really see that beam-leaded part, here's a picture of one. And since we didn't cover much on that, Al and Gary ginned up this morning a plot on the HP parameter analyzer of a forward on a silicon device for you to stare at, and you'll see the oft-quoted 0.7 of a volt turn me on that current scale. Incidentally, when we cranked that up, we cranked it up to zing a specific person who gave us a small smile. But the Unitrode salesman thought it was great, and he conned me out of it. He carried around for 2-3 years to sales meetings and whatnot, just to kind of shake people up. What are you going to see when you find one of these things finally listed somewhere, or somebody says, I need this thing, and you have to go find out what it is, or you're looking for one to use for some purpose? And you'll find in these fun sheets two things. You'll find ratings, and you'll find parameters. And ratings, to a first approximation, are probably not very negotiable. A lot of that is fixed. It's a function of the package, therefore the dissipation is no more than so much. And surge ratings, if you want to run more than they say, you're going to burn it, whatever. But there is a distinction, and I wanted to point that out if you get pawing through a spec sheet looking at these things. PIV means whatever you want it to mean. Most people will quote one, and you look at it and you say, golly, that's just fine. That says 100 volts, and I'm going to run this thing at 100 volts, and we're in great shape. And it turns out that the lowest breakdown voltage they've got in the box is 112. And you say to yourself, nah, I don't want to, I'm not going to run that close to disaster. I needed the lowest one to be 140 or whatever. I'd treat it like a rating, Fine, it's on the sheet, but don't bet the program on it.
What's PIV stand for?
Peak inverse voltage. Generally, we try to run, when we have the luxury to do so, parts at not more than 80% of breakdown. And breakdown, on any reasonable device, for a rectifier at least, has a positive temperature coefficient, which says that as you go to cold temp, the breakdown will decrease, and one needs to watch that if you're close to the mark. This is a rating common for rectifiers. excuse me, and is, as I say, the peak value of these string of half sines at 60 hertz divided by pi. Half wave average rectified, they call it. And the leakage, as you would expect, is the current that flows when you back bias the device at some specified voltage at some specified temperature, and sometimes for some specified length of time. In a forward, the same way, you really need to specify current and sometimes time to make it meaningful between user and builder. This also, the forward, I should mention, has a negative temperature coefficient at reasonable device currents. And it does go positive if you run the device at too high a current. And we do that sometimes. But the temperature coefficient of the forward is a function of the current. And the capacitance, as Dr. Dawes mentioned yesterday, you have a capacitance associated with a junction. And on the smaller devices, at least, normally this is specified. Normally given at zero bias. It is a function of bias and decreases with increasing bias. If that's a mystery, that's because this depletion region he was drawing at you about is becoming wider as you increase the voltage, so the capacitor plates are further apart and the capacitance goes down. Reverse recovery time briefly means putting the device in stable forward conduction, driving it with a pulse source of some sort as quickly as the equipment will allow into reverse conduction, and then waiting to see how long it takes to turn off. That's usually specified somewhere out in here, and the guy says, well, I want it off. And you say, well, you can't have it, and the reason is you need a place to which you can reasonably measure. If you get over in here, you don't know where you are. You can't read it on the equipment. So it's usually specified well down in here so that you can find a point on the scope to do the measurements. Incidentally, and I'm sure the RF folks will talk about that, if you do that very quickly, the device doesn't know the difference. It's just fine. I'll pass current the other way. I don't care. Because you had it pumped full of carriers and it's ready to go. Well, if you again very quickly change your mind and drive it back up here, it still doesn't care, within reason. If you do that extremely quickly, now we're talking RF. You're going to run it through there. Doesn't care. Now we turn the diode off with DC, and you can't do that anymore. We've got an RF switch. They talk about that. Or a switch to control RF current flow is a better way to put it. Many manufacturers don't specify this. My picture ended up on the next sheet. I suddenly panicked here. What we're saying is, if I quickly drive this thing into conduction when it has been off, what's it going to do? Well, there are two things specified. How high does the voltage go before it settles down to a steady state value? And at what point in time does it do that? Well, here's the time business here, and we specify some fixed voltage and it's appropriate for the device at some specified current, and you say, fine, I'm going to watch it till it gets back to there, and that's going to be my time. As you can see, I implied it's still not back to its stable, steady state value. And again, the reason is you need some place to which you can measure. If you put this value out here, you can't find it in a practical measurement sense. And the same thing is true on how high did the voltage go. Well, to try to not leave it open to operator interpretation, you set the time and say, whatever the shape of this thing looks like within reason, find that time and tell me the voltage. So, conceivably, this thing could do this. You see what I'm saying? It's not an absolute guarantee, but it's an approach that's been settled upon as something that can be done at a price that somebody's willing to pay to get some sort of control on that parameter. And one device for which it was spec'd, I just picked the numbers out to show you. On this gadget, this was TFR. They're saying 15 nanoseconds. And VFR, which is the high point, they're saying 1.5 volts. And on the first circuit there, the recovery time is 35 nanoseconds. This is a 20 amp device. Those sorts of things, if important, you sometimes find, not always. This one, again, is another rating, and it's almost always done as 1/2 cycle of power line, 60 hertz. So it's a half sine of current, and they give you the peak value that their little gadget will take reliably. I went through a number of types here. I'm not sure how much profit is in that. I don't plan to read all that to you. But generally, for the classification of rectifiers, at least in the data book, they do not specify recovery time. Implication is these are gadgets that are used at line frequency, and most anything is good enough. If there is nothing done to speed it up, and if it's a reasonable sort of a device, and that's hard to follow up and say, what do you mean by that? Garden variety things. Day to day, up to a few amps. Not that big door knocker on the end of that battery cable. I'm not talking about that one. You'll note there was a time written on that that said 15 microseconds. That doesn't belong in this class. Okay? That's part of my arm waves. You can't cover everything. At any rate, 1 to 3 microseconds. And there are some truly that are much, much longer than that. And again, I did an arm wave here for trying not to exceed 80% of breakdown if you have the luxury and the environment permits it and all that sort of thing. Hit you again with the temperature coefficient being positive, which hurts you at cold temp. And you can trade off, generally, everything else being equal, breakdown voltage capability for radiation tolerance. First approximation. The higher the breakdown voltage, everything else being equal, the higher the resistivity of the material will be, and the more it will suffer from neutrons damage. I did a little exercise here on the back 2 pages of that big pile I gave you. And the last 2 pages, incidentally, are not numbered. The next to the last page should be a plot. And I picked these numbers off of there, and that's a cheat chart I keep around as a rule of thumb sort of thing. And you'll find that if you look, we can work it backwards. I don't happen to have it lying here where I can see it, but if you look on the left-hand side at the top of the page, you'll see 1,000 volts. Is that right? And that intersects one of those lines out there somewhere, that breakdown curve. V sub A, it's labeled with a double circle around it. That should be an impurity concentration of about 2.5 10 to the 14 along the bottom scale. Is that right? Okay. So we had a 1,000-volt junction. And again now, I'm arm waving at you, you see. That's a lot of assumptions, and that's the product that this fellow was talking about when he drew this plot. But nonetheless, for comparison, 2.5 10 to the 14 impurities per cc. That's impurity concentration along the bottom. Now, if you play the same game with 100 volts, you should end up at about 5 10 to the 15 for an impurity concentration. Now, if we whack this thing with a cup full of neutrons, and if you will permit me a rule of thumb thing that says I'm going to effectively remove one carrier for every neutron, loose terminology, it says I'm really going to take a big fraction of the 1,000-volt material carriers out of there, 40% of them. And it's a very small percentage in the 100-volt material. And if you want to look sometime, of course, if you get down to 10 volts, it's even more impressive, see? If you can build 10-volt stuff, and you don't have to worry about neutrons much anymore. You worry about other things that are going to eat you alive, and there are other things. But that's the reason that plot is in there, and if you forget how to do that, and I do every time I use it, the how to use it is on the next sheet. But it is kind of handy just to get a seat of the pants feeling about how those numbers look for different kinds of material. I got carried away there and didn't talk about this. And it's really another arm wave. But generally, the kinds of applications that we're working with here, people are worried about surges or multiple surges, and not so much about, gee, will this thing make DC out of AC at some current level reliably for a long period? Generally, we don't do that. I'm not saying disregard it. I'm just saying that generally the kind of information that our customer wants isn't in the rating sheet, because the rating sheet was aimed at the guy that's building a power supply, and he wants to know if it'll run for 2.5 years under adverse conditions at 20 amps or whatever. And we're more worried about shorter term sorts of things. This was kind of a digression, I guess. Some manufacturers put these in their dope sheets and some don't. But generally the plots, they will range from maybe a 1 or 10 nanosecond pulse width to 10 milliseconds. But they generally chop off at 10 milliseconds. And the reason is that that's high enough to get this number included, which is right back to the guy with the 60 hertz job. They got him covered and they quit. And I'd like another 3 orders of magnitude on that plot, because that's where a lot of my customers are interested. Incidentally, I did do some looking, and that seemed to be typical looking at 2 or 3 people's rating sheets. So if the thing is rated at 5 amps average rectified on the spec sheet, you can figure 15 to 30 times that number for a single cycle surge rating. In a little box, if you got to look at it there, where the little black blobs with 2 wires are some various shapes of high voltage assemblies we've used. And we have thus far kept out of trouble by using devices with nice square breakdown knees and reasonably good matching among them in the pack, so that we didn't have to, and that may, some people call it balancing, I said ballasting. It's some outside influence, resistor string or capacitor string, to try to force equal voltage on each device. And we don't put those in here. And we've gotten by with it so far. Another class which is described as a fast recovery device, and these are rectifiers. And those numbers generally are tens to hundreds of nanoseconds for reverse recovery time. Most commonly used speed-up approach, at least for the fastest end of this material, is gold. Some people are using platinum, which allegedly gives you a better reverse characteristic than does the gold in terms of leakage. Somewhere in here I said, and I've already forgotten where I put it, but it's in there in writing, that everything else being equal, you build two diodes, you gold dope one and you don't gold dope the other, the gold doped one will have a higher leakage, reverse current. And supposedly the platinum doesn't give you as much problem with that. That's hearsay. I never built one. And the people that originally were using platinum wouldn't tell me they were using platinum. I found it out by accident later. Anyhow, switching diodes as a class, pretty much I think at 150 volts you could chop that off, and that's arbitrary on my part. If you want to say 100, say it. If you want to say 200, say it. But I don't think I'd go beyond tens of nanoseconds in terms of recovery time to fit in that class.
Right at the top of the screen, look, quenching. What's quenching?
Literally that. I think in the ingot, make it hot and quench it. And I am told that freezes in defects, structural, that act as traps to kill a lifetime. Somewhere along in here, I thought I had said lifetime a lot of times, and I've been jawing at you without reading all these words. Maybe I have, and just didn't realize it to this point. But in case, whether I have or not, I don't want to forget. Lifetime, when I say it in here, is another arm wave. It should be, to be complete and accurate, minority carrier lifetime. There was my statement about leakage. Zehners. In general, I'm going to use the word Zener for all these things, whether we're talking about something that works at 2-3 volts or at 20 volts. The purists will argue, oh, no, below so-and-so voltage, that's Zehners, and above that it's avalanche. Well, I guess they're right. But in the middle, it's both, and to different degrees depending upon where you are, and to some extent upon who built it and what process they used. When I say Zener, I mean any of them. It's a thing you use, you put a resistor in there and you put volts on it, and you get a constant voltage out of it. And I put down some numbers here, and it's still part of the arm wave, and I admit that. You know, you can get a different number from a different set of data. Look at somebody else's product, and their number's a little different. So 5 is not magic and not absolute by any means. It's around there somewhere. And the same is true of this other limit. How do you finally tell when that mechanism is not there anymore? Well, I don't have time to care. Anyhow, this was an attempt to give you a clue. The stuff that is suffering from true Zener generally has nice soft knees instead of being a nice square characteristic on the curve tracer. It looks like a quarter circle. And the customer's unhappy and says, now wait a minute, I wanted to run that at 10 microamps, and it doesn't get to be straight up and down until you get to 10 mils. Well, that's, you know, go to somebody else's diode store, but that's the way they are. Now, there are ways around that. People now build integrated circuits which to the outside world look like Zehners, and they look very nice down in there. They don't do so well in radiation, so you always pay a price somewhere. Okay, the point here, I guess, that really matters is that's somewhere around the 5-volt range, we get a change in the sign, that is the direction, if that's a better way to put it, of the temperature coefficient. Devices below about 5 volts have a negative temperature coefficient. You make them hot, the voltage goes down. Above that point, it's positive coefficient. You make them hot, the voltage goes up. And everybody says, gosh, I need one at 5 volts. Just buy me those right there, and I'll live with them, and I'll have a 0 TC for free. We tried it. It maybe it's been done successfully, but when we tried it, it turned out that at least this manufacturer's product at that voltage was current sensitive. That is, the temperature coefficient was. Generally in Zehners, it is not too much, but these were. And we went through a whole bunch of lots before we finally got him enough parts to finish his project. So it sounds good, and maybe you can make it work, but in that case it was a large pain. Well, anyhow, the kinds of things that are specified are maybe obvious, and not too many for a two-legged part, which, well, Al will cover that tomorrow. I was going to mention how complicated these are, but Al Ossemeyer plans to tell you all about that complexity business tomorrow. Zener voltage with a tolerance stated, 5%, 2%. Incidentally, common everyday things, 10% is no problem. Pay a little more, you get 5%. You want to cut that to 2%, you double the price. You want to cut that to 1%, you double that price. And so on, and so on, and so on. It doesn't take many of those before it hurts. Incidentally, it is also very difficult to get some people to test them if you decide that your circuit just absolutely won't work with anything less than a 10th% tolerance on the Zener voltage. Everybody's tester is cranked up to do lots of parts, not precision work. And it'll be somewhere between impossible and extremely expensive and very slow to get anything that's very tight, say beyond about 1%. You can, all you have to do is pay and wait, but those two things may be hurting a good bit before you get it done. Capacitance. If you're in a DC situation, you don't care. A lot of the Zehners that we care about here are used in applications where we have pulses flittering about the circuitry, and people do care. Sometimes this is not specified. Depends upon the part and what it looks like. The smaller ones, generally, you can find it. The bigger ones, nobody cares. Again, those were parameters. Here are ratings. It's in a so-and-so package, and the package is good for so much. That's the rating. And again, the surge. I didn't do any look-see on that. I have not even a guess to give you. Sorry about that. I would guess it's not as impressive, and that is a guess, as it was on the forward. But I didn't look. These are things that we are using some of, have for a long time. And what it amounts to is to balance the positive temperature coefficient of a Zener at some voltage, and I picked this 5.7 because the numbers come out easy to figure, against the negative temperature coefficient of a forward junction. We can find two of those, one positive, one negative, same amount. We put them together, and when we change the temperature, the voltage shouldn't change. At least that's the theory. Then it works. But it has some problems. One of them is that the temperature coefficient of the forward, as we mentioned earlier, is current sensitive. As a consequence, If you want the best performance that you can, that particular device will give you, you're stuck with a fixed current. Now you can use them over wider ranges and they're still compensated to some degree, but you don't get the ultimate performance. Now, I picked that as an example. There are others, and I went through some arm waving on you here to show you the possibilities. The point to make, I guess, is if we're going to compensate with forward voltage, junction, temperature coefficient increments, we have to do it in increments. You put in a forward, you get, say, 2 millivolts worth of negative per degree. Then you're stuck. You have to go up the ladder of positive TCs far enough that the next one has a +4, because you can only add in increments of 2, and I'm being arbitrary, but 2, so we've got to add 2 forwards. So we've left out all those in between over here on the Zener side that we can't compensate. Well, that isn't literally true, because right here I gave you 2 forwards and 2 different voltages. And one of the reasons is that the Zener junction in these 2 cases came from different processes. One is alloyed. You remember we talked about that a minute ago, where you drive the aluminum in to form a junction. Incidentally, the reason those are used in low voltage, particularly Zeners, is that they are very abrupt. The change in doping, purity concentration, is very abrupt when you do an aluminum alloy junction, much more so than a diffused device. And as you recall, Dr. Dawes, I think, said yesterday that the breakdown characteristic is a function of that gradient. How quickly can I change from P to N? If you take a 1.5 feet through the material to do it, someplace it's going to break down, but it doesn't know where. And if you do it, theoretically, in no distance, you get a sharper characteristic. That's the reason that these are different. Okay? The process yields different stuff. Isn't this exciting? Anyhow, again, I picked out some numbers. There are exceptions. Some people's process yields different things. You may find another voltage tucked in there somewhere, and I didn't tell you about it. So I'm saying this is by no means absolute. It's a general idea of the way they work and kind of what you can get. I mentioned also somewhere here that there's another compensation scheme. I think it is not commonly used, but that is, instead of using forwards for compensation, use a Zener with a negative TC, one of those below 5 volts, and another one with a positive TC that matches in magnitude, 7 or 8 volts. Put those 2 in series. Don't use any forwards. It's possible. I think if used, it's probably on the higher voltage stuff, because you gain volts a lot quicker that way than putting in forwards. Yeah, that's an arm wave too. Typically, the tight end of the spec on these is 0.305% per degree C on the super end of the whatever voltage you're talking about. What is that? That's 5 parts per million per degree. Microvolts per volt. 30 microvolts per degree on the 6.4. Does that make sense? John, keep me honest. You were supposed to be ticking that off. All right. Radiation tolerant TCs. We're horsing around with one, and what the vendor is doing is the compensating junction that he's put in to try to balance out the positive TC of the Zener junction. That forward he has gold doped. Now he obviously doesn't care about speed, but in first approximation what he's done is screw up the lattice thoroughly with the gold, which Dawes mentioned goes in usually interstitially. And when the neutrons come floating through, the thing is already so thoroughly screwed up with the gold that that neutron damage effects are not as evident. That's the approach. Incidentally, you can pay almost anything you want for one of those. Depends on how fancy you want to get with the numbers. Transient suppressors, at least, yeah, I was a little too general here. There is a class of parts called MOVs. I don't know whether anybody's familiar with those. They're metal oxide varistors, and they come in various sizes and shapes. I think a common one looks like a ceramic capacitor, and it's got a couple of wires, and you put it across the terminals you want to protect, and when the surge from the lightning comes down the line, it swallows it and saves your hi-fi or whatever. I guess in a loose sense, those are transient suppressors. What I'm talking about is a class that most people have begun to call transorbs. That is a trademark of General Semiconductor. But they're Zehners. Single junction, several packages worth in a blob, all kinds of combinations to get more volts and more watts. They're Zehners. And one of the things that I've been weak on here is to show you physically how these things look in the package. I passed them around. They're difficult to see. But they will take something like that 1/4 inch diameter, 3/4 inch long metal package that I passed around with axial leads on it and stack a silicon chip, a metal disc, a silicon chip, and a metal disc. Try to get the heat sink next to the silicon as best they can for surge energy absorption capability. The pin that I'm fooling around with has sure enough an I layer, but in fact it's N, not I. It's not much N, but it's N. And I think that's a reasonably complete explanation. They deplete at a fairly low voltage. And since the output of photocurrent is a function of gamma dot, is a function of the depletion region volume, we deplete it at a low voltage, then the volume isn't going to change significantly. We run it over a voltage range above that, and that voltage can in fact vary within that range, and the output won't change significantly. Is that an arm wave? Does that mean anything? Everybody thinks, I put that in. I think that's a cute symbol. But those are 4-layer parts, and the floor knows all about those. I think what it is a gateless SCR. And constant current diodes are in fact FET chips with the gate shorted to the source, so that you are looking in fact at the zero bias characteristic of a FET, JFET, when you have a constant current diode. At the back end there is that plot, which I find handy sometimes. I'm at a stopping point and we're out of tape. Thank you.
Any questions?